Hello everyone. Let's start today's session with Professor Hariharan Narayanan. He'll be giving a short talk on sums of GUE matrices and concentration of hives from correlation decay of eigenvalues. Let's welcome.
Thank you for the opportunity to speak here. So my title is Sums of GUE matrices and concentration of hives from correlation decay of eigengaps. This is joint work with Scott Sheffield and Terence Starr. So I want to start with what a hive is. A hive is a combinatorial gadget. It's a pattern of numbers. So you have an equilateral triangle like this with subdivided n times. And you write numbers from on the boundaries in such a way that their piecewise linear extensions are concave. So here, for example, the gap 65 minus 0 slope is greater or equal to the slope from here to here, which is 55. And this causes the numbers, when you piecewise linear extend them, to form a concave line. Concave curve. And this is true for each of the boundaries. So here, for example, in this hive, the lambda is 40, 30, 20, 10. That represents the fact that this slope is 40, this slope is 30, this slope is 20, this slope is 10. Mu is again 40, 30, 20, 10. It represents the fact that this slope is 40, this slope is 30, this slope is 20, and this slope is 10, and this last side being 65, 55, 45, 35, represents the fact that this slope is 65, this slope is 55, this slope is 45, and this slope is 35. Now, what we have to do is we have to fill the.
What do you mean by why is it a slope?
So I'm just saying that this is a unit. Each of these is a unit edge. So when I write two numbers here, I can talk about the slope if I piecewise linear extend to the line segment here. So this has become a line of slope 65, because it goes from 0 to 65 in unit length. That's what I mean by slope.
So I should look at it as something in 3D.
Yes.
65 is the height of it.
Yes.
Okay.
Yeah. So these numbers will now be.
It's also directionally assigned. Because you're going in a particular order.
Yeah. So I did mention that, but lambda is going from here to here, mu is going from here to here, and last side mu is going from here to here. Yeah. So there is an order. And in order for it to be a hive, I have to write numbers in the interior vertices in such a way that when I do the piecewise linear extension to the entire triangle by doing piecewise linear extension to these pieces, I get a concave surface. Now, of course, this would only be true if restricted to the lines you had concavity. Otherwise, you're not going to be able to extend it to the interior to get a concave surface. And that's why you need the concavity of the boundary values to start with. So this is what I call a hive. In practice, I mean, the concavity is implied and is implied by certain rhombus inequalities, which means that for every unit rhombus like this, the sum of the entries on this shorter side has to be greater or equal to the sum of the entries on this longer side. So, in the context of piecewise linear extensions of such triangulated large triangles, concavity is equivalent to all these rhombus inequalities being satisfied. So, are there any questions so far?
I don't understand the blue numbers. Hardly 101.
So I'm just writing them in some way so that all these rhombus inequalities are satisfied. So for example, I needed the fact that 100 plus 150 is greater or equal to 125 plus 120.
But these numbers are unique.
They're not unique. But they cut out, the inequalities cut out a polytope. So the set of possible hives from the polytope.
So I understand this triangular numbers you said, but what's hive again?
So this is a hive. What I've given, this array of numbers would be called a hive. And when I fix the boundary values, the possible values in blue form a polytope given by these inequalities, and that will be called the hive polytope.
What are lambda mu?
Lambda mu nu are the slopes corresponding to the boundary. So the boundary is fixed beforehand. So this lambda is 40, 30, 20, 10. This is the slope of this is 40. By slope, I just simply mean 40 minus 0, and this 30 is simply 70 minus 40, and so on. Yeah.
Another question for my understanding. So you define it in a discrete manner, you have steps of unit length.
Yes.
But suppose it was continuous, what would be the picture in that?
So if it were continuous, then you would have a continuous triangle, and for every rhombus of arbitrary size, you would require that these inequalities hold.
But what would it look like in the 3D?
It would still be a surface, it would be a concave surface, yeah, over a triangle. No, because these rhombus inequalities for concavity, they are stronger than concavity.
Okay.
The reason it becomes equivalent is that here this is a triangulated setting.
Okay.
Yeah.
Okay. Do you have is there some stronger notion than concavity that captures it?
So we call this rhombus concavity, which is simply that whenever you take a rhombus in this picture, this plus this has to be greater or equal to this plus this.
Okay. Okay, so it's that.
Yeah. So Lucian and Tao invented hives and used them to prove something called the saturation conjecture for little rejection coefficients. Together with the work of Klartag, this implied the Horn conjecture, which gave a description of the possible spectra of x plus y, where x and y are Hermitian matrices with spectra lambda and mu. Yeah. So this picture actually has significance for linear algebra. Namely, suppose I want to know if I have two matrices, two Hermitian matrices with eigenvalues 40, 30, 20, 10 and 40, 30, 20, 10, what is the possible set of eigenvalues of the sum? So a particular vector mu can be attained as the eigenvalue of the sum of these two matrices if and only if it can be extended to a hive. So then it solves the Horn problem. So these in the original works, they actually work more with honeycombs, and I want to describe this object as well, although we won't work with it because I think it gives a feel for the surfaces. So these concave surfaces have slopes at any triangle, and this, if you just draw points in the plane corresponding to the slopes of those concave surfaces. So, for example, this is the slope of the triangle on the very top. So here you have a triangle that has a certain slope viewed as a graph of function over R2, and that slope is a point which we will plot in the plane here. Similarly, this is the slope of the triangle immediately below it. So those points form a nice honeycomb, and the reason they form a nice honeycomb is that this is going to be vertical because if you have two triangles, like the graph of a concave surface over a triangulated big triangle like this, then the difference between the slopes of here and here will have to be vertical because the two triangles agree on this horizontal line.
What is the scope of that? The triangle has 3 edges, right?
Triangle has 3 edges. So I'm thinking of this as a concave surface like this.
90 is the height.
Yeah, 90 is the height. Yeah.
So the slope is in the direction of the normal of that thing.
Not normal. I'm talking about think of the function. So the gradient. It's a vector in R2.
Yeah, it's a vector.
So for that reason, because these two triangles agree on a horizontal line, it forces the difference in gradients to be vertical. And similarly, for similar reasons, these angles have to all be 120 degrees. And this honeycomb was what they work with. These semi-infinite lines are indexed by the eigenvalues or the slopes of those little pieces. And so this lambda 5, for example, is this gap, 100 minus 90 equal to 10. So you can think of it either as a honeycomb or as a hive. You'll always be thinking about it as a hive. I just wanted to mention it. Okay, so the initial way they came in is through this representation theory of the general linear group, and it not only are these polytopes important in terms of their real points tell you something about eigenvalues, but the integer points in these polytopes, when the boundary data are integral, tell you something about the representation theory of GLN. It tells you if you take the tensor product of two irreducible representations and you decompose the direct sum of irreducible representations, how many representations of a particular type appear. So this saturation conjecture which they prove is a statement that these polytopes, when the boundaries are integral, have the property that if the polytope is non-empty, then they definitely contain an integral point. So this is an equivalent way of stating the saturation conjecture. So this is a very special family of polytopes which has the property that if the polytope is non-empty, it definitely contains the integral point. The polytope of hives with given boundary data.
Integral.
The integral boundary.
So that's the set of selection we get from the Romulus patterns.
Yes. So these Richardson coefficients are also counting the number of square triangle tilings in certain domains, and there was an equivalent formulation in terms of puzzles which are labeled tilings of certain triangles. So I just have mentioned that this to tell you that there are lots of connections with other tiling kind of problems as well.
So these polytopes have an interior point essentially.
Not necessarily, because the polytope can be non-empty. I mean, it can be empty.
Thank you.
But if they are non-empty, they contain an integral point.
And there are basically the scaling contain an integral point in the original thing also.
Yeah, because the polytopes are rational. If they contain a real point, they contain a rational point. And therefore, if you scale it, you contain an integral point, and therefore the original contains an integral point by the saturation. So this is actually the original way in which Richardson coefficients were defined was using tableau. And this picture actually tells you how to go from a tableau like this to a honeycomb. And this is a proof by picture that tells you that this counts Richardson coefficients in the integral case. So we'll be interested in the random matrix angle here mostly. So not only do these hives tell you something about when you have a matrix whose spectrum that is the sum of two matrices of given spectra with a given spectrum. It also tells you that when you have a natural measure on these matrices. So if I take a random matrix with spectrum lambda, a random matrix with spectrum mu from the unitarily invariant measure, Hermitian matrices, and I add them, I get a measure on possible matrices, and you look at that spectrum. That's some probability distribution over spectra. But the same picture gives you a characterization of this measure as well, and we're going to use this to study the hive as a motivation for studying hives in a probabilistic setting. So this is just the horn polytope. It's the projection of the hive polytope onto what you see on the third side. So that hive polytope is this nice polytope defined by a few inequalities. If you're interested in what is the possible spectrum of a sum of two matrices with given spectrum lambda and mu, that is a fairly complicated polytope with exponentially many inequalities. But it can nonetheless be expressed as the projection of the hive polytope onto the third side, which has just n pieces.
So the correlation is leading to Richardson for all outcome of this work, is it?
So that came first actually, and then together with some work of Clash, it implied the linear algebra setting. Yeah.
That came first.
That came first. So this natural probability measure on the horn polytope will be referred to the horn probability measure. It's simply what you get if you take two random matrices with spectrum lambda and mu that are independent Hermitian matrices, add them and take the spectrum. This is the horn probability measure. It is supported on the horn polytope. And this has a nice closed form expression. The density of that horn probability measure has a nice closed form expression in terms of the volumes of the hive polytopes. So it's basically the volume of a hive polytope, but you weight it by some van der Waals matrices, by van der Waals determinants. So this is the probability of observing mu when you add two random Hermitian matrices with spectrum lambda and mu. You take the volume of the hive polytope corresponding to this, you multiply it by the van der Waals for mu, multiply the van der Waals for tau, where tau is this matrix, divide by the van der Waals for lambda, divide by the van der Waals for mu. Yeah.
So basically, you first create a hive with size lambda, mu, and mu. That makes a polytope. You take its volume and
No. So that hive that you construct is one point in the hive polytope.
Right.
Is that what you meant? So you get a concave surface. With that concave surface, you should think of it as a point in the hive polytope.
But nu is a particular point in that polytope.
So nu is the evaluation of the hive on the third side.
Right.
So this is a point. This point is a point in the hive polytope, this concave surface. When you evaluate this point on a third side, it's like restricting the coordinates from subset of the coordinates. So geometrically, what that corresponds to is you have this polytope and you are projecting that polytope down to some lower dimension and looking at that projection. So that is, yeah.
The number of matrices with the given spectrum mu, is it finite?
No, it's infinite because you can conjugate the unitary group.
You are choosing uniformly at random.
Yeah, so it's uniformly at random from a continuous space.
So about computing the volume of that hive polytope.
Yeah.
So what you mean, I'm just asking, like, so you define this hive polytope and in the agent you put lambda, mu and mu, and then you take the volume of that.
Yes, that's it. Okay, so now there is a related question called the Schumann-Horn problem. I want to spend a little bit of time on that, but I won't spend too much time on it. Basically, the idea is that there is a kind of degenerate hive called a Gelfand pattern, and what you do there is you take eigenvalues of the matrix here. You draw them on the edges. These are the eigenvalues, and then you take minors of the matrix and do the same. And this is one way of producing what's called a Gelfand pattern. It has a certain interlacing property, namely this will be greater or equal to this will be greater or equal to this, and so on. They are also observed as from a hive. So if you have a hive and you look at the slopes of just the horizontal lines, you get a Gelfand pattern. And if you want to know whether a particular spectrum matrix can have a particular diagonal, a Hermitian matrix, a particular spectrum can have a diagonal, that corresponds to a similar question in this world of Gelfand patterns. So basically, if you can write down a Gelfand pattern with such values in such a way that the sum of these things minus the sum of these things is equal to one of the diagonal entries, the sum of these things minus the sum of these things, another of the diagonal entries, and so on, then you can get that particular diagonal. So the Schumann-Horn problem has a solution in terms of this Gelfand polytopes. So here, for example, this pattern certifies that there exists a Hermitian matrix with eigenvalues 15, 5, minus 15, whose diagonals are 3, 4, 3, and minus 10. The 3 comes from here, the 4 comes from this 7 minus 3, this 3 comes from 10 minus 7, and this minus 10 comes from 0 minus 10. Okay, so just as this hive polytope, a point in the hive polytope certifies that you can have a triple of matrices with certain eigenvalues which add up to 0, or alternately the sum of the first two is the third. Similarly, this picture can tell you, this picture can tell you whether a particular diagonal is achievable for a matrix of a given spectrum. So what we are going to do here is we're going to look at Gelfand patterns as hives, because basically there was a weighting term in the measure of V of nu. When I wrote, V of nu times V of tau divided by something times the volume of the polytope, and that weighting factor has to be, incorporated into the formula in a geometric way, and that's why I need these Gelfand patterns, because the volume of the space of Gelfand patterns, the given bottom row turns out to be basically a van der Waals determinant. So this is going to be some sort of, we're going to augment these hives with a van der Waals determinant volume Gelfand pattern. So this is a hive with the same boundary conditions. This is a augmented hive where you have a hive here, and here you have basically a Gelfand pattern which has somehow been bent into a hive by putting large gaps lambda here. Okay, so you should think of this as a Gelfand pattern, but for technical reasons, we want it to be a hive. So we have basically put really large gaps between this, and thereby this Gelfand pattern has been converted into a hive. So secretly this is a Gelfand pattern, but it's a hive here, and so is a hive here. Lambda mu is mu, we have already discussed. This is a large fixed thing, and this A will be free. So what is special about this? I now have a polytope which has hive constraints on this part, Gelfand constraints on this part, and if I pick a random point on this in this polytope and I just look at what happens on this third side, mu, it's an internal variable in some sense. The probability distribution of that mu is exactly the same as the probability distribution of observing a spectrum of mu when I add two random Hermitian matrices with spectra lambda and mu. So this picture now takes into account that weighting factor and is related to the linear algebra problem in a direct fashion. Otherwise, there was this V lambda beta which had to be handled somehow. Okay, so there are results in free probability which tell you things like if I take a set of eigenvalues which are very close to a given curve for lambda and for mu, then there's some concentrates around a fixed spectrum. And this is motivation for asking, do you have this sort of concentration also at the level of hives? So that free probability result that I told you will tell you that when you fix lambda and mu, basically this thing that you observe on this third side here does concentrate. It's every time you take a random point in this polytope and you observe what happens on this line, it is with high probability very close to a certain fixed curve. But this is not known for this entire thing. We only know it for the third or the middle side here. So we would like to say it's true here as well.
Sir,
yeah.
What do you mean by fixed curve? So there is some expression involving lambda and mu around this concave.
Yeah. So there is a fixed curve. You should think of this now as a fixed concave curve. And every time you fix a n, you subdivide it equally and you do a piecewise linear extension. And that's how you get lambda and mu. So yeah. So we are interested in whether this entire hive concentrates, and we are not able to show this in general, but we are able to show it when these distributions of the lambda and mu come from some very special distributions called the Gaussian unitary ensemble matrices distributions. So these are basically random Gaussian matrices where each entry is an independent Gaussian. Individual entries are mean zero variance one complex. Their conjugate transpose has to be identical to original matrix. That's considered for Hermitian matrices. But the diagonals are real and Gaussian of mean zero variance one. The non-diagonals are mean zero and variance one, and they equal the conjugate of their partner on the other side of the diagonal. So this is the explicit form of the eigenvalues of a GUE matrix. So note this V lambda squared here, and there's an exponential term as well, but there's V lambda squared. So if the van der Waals determinant corresponding to the eigenvalue is big, that's an indication that it's more likely to see those eigenvalues. So this measure is now no longer a measure on this polytope because lambda and mu are not fixed; they are random from the GUE measure. They're very close to fixed because the GUE matrices have a spectrum that is very close to something that comes from the so-called semicircle law. So they're essentially fixed, but there's a little bit of randomness. So you should think of this as a measure not on a augmented hive polytope, but rather on a cone where you're permitting these to vary as well. But they're in practice, they're very close to this. There's a kind of smooth analysis of the case where this mu and mu come from a certain semicircle law. So this probability measure assigns a constant probability to each polytope. So this cone, if you think of this as a cone, but when you take sections of this cone, you get a polytope. And for each point in a fixed polytope that obtains in this fashion, the probability density is constant. So it's sort of along slices, the probability measure is constant. So this is our main theorem that in fact, when you look at the vertices of this hive, you do get some kind of concentration. The typical value of the hive is order n squared, and what we can show is that the variance is little o n to the 4. So that means that the standard deviation is little o n squared, and you have some kind of non-trivial concentration. This is the main result. Are there any questions regarding the main result?
We believe this is true for all distributions, and we show it only for deviations.
So this is a simulation by Alok Gangopadhyay on, so he created this GUE hive with n equal to 250, and he'll talk more about this in the next talk. So this is how they look generally. So this is that surface, the 3D surface that we talked about. And you can note that this curve here has a height that is roughly 1 over √2 times the height of this. And that is not a coincidence, because if you take two GUE matrices with standard deviations 1, when you add them, you get a GUE matrix with the standard deviation of √2. So it just gets scaled up by √2, and this is observed after we do the simulation. So how much time?
5 minutes.
Okay. So in the remaining 5 minutes, I try to give a hint of the proof. So this in principle, this in particular does not follow from some earlier work with Sheffield, which was on large deviations for random hives. I just wanted to mention this. So there is some new thing in this. So what is the method of the proof? So basically, the idea is if you want to prove that a certain random variable concentrates, one way of doing this is to view this random variable as a Lipschitz function of a log concave density. Because log concave densities have nice concentration properties, and Lipschitz functions of these log concave densities exhibit concentration. So that's going to be the strategy. We're going to have this log concave measure that is given to us. It is simply basically it comes from the GUE measure somehow. But we will view this vertex value at a given point in the hive as a Lipschitz function of a certain log concave measure, and that's going to lead to concentration. So what is the Lipschitz function? So the Lipschitz function comes from something called the octahedron recurrence. So what you do is you put two Gelfand patterns here and here. You bend them to make them hives. Okay, so this is mu, this is nu. You put a Gelfand pattern here, a Gelfand pattern here, and then you perform a certain piecewise linear map. It's not a linear map, it's only a piecewise linear map. And that actually gives you an augmented hive with the right boundary conditions. Okay, so here you have a log concave measure, here you have a Lipschitz map. And if you can prove that this log concave measure has the right concentration, this Lipschitz map has the right Lipschitz constant, you get concentration for this. And that's the general strategy. So this is the base of the log concave measure. It's basically two Gelfand patterns with these creases here to indicate that you're putting large eigenvalue gaps to make them hives. And basically, in just saying that this is a Lipschitz function from this log concave measure, and we have to prove some things about the Lipschitz constant of this octahedron recurrence, and also prove something about the concentration property of the log concave measure, which incidentally uses a result of Klartag. So this is about what the nature of that Lipschitz map. It is actually the maximum over the weight of certain matchings. Okay, so this is that Lipschitz map measures the weight of a certain matching with respect to random edge weights that come from the Gelfand pattern. Okay, so this Gelfand pattern somehow assigns random weights to the graph, and then you take a maximum weight matching, and that is actually the value of the hive vertex. So it's a very nice result due to Speyer. If you want to prove the concentration of the supremum of a number of linear functions, because for every fixed matching you have a linear function of this log concave measure, But when you take the maximum weight matching, you get a convex function of the log concave measure. And you need to prove the concentration of that convex function. And this follows from a result of Klartag, which says that basically if you have log concave measures with nice covariance matrices, then their Cheeger constants are also lower bounded nicely. Okay, so this is a very nice recent result of Klartag on the KLS conjecture, very powerful result. So we are able to use this here.
There's a log improved with all the improvement.
No, this is the final version. Otherwise, there were other things. Like Chen's result has, yeah, this is the final Klartag result.
Oh, what is the latest?
This is the latest. This is the latest. Yeah.
But the other ones differ only by the log. Like
Yeah, the other thing has something sub-polynomial instead of the log, and that would also be good enough for us. So in order to prove that the variance of these linear terms is right, there's a log loss, but you have to prove that the variance of the linear terms here is order n to the 4 minus something that is non-trivial. You don't need this kind of constant here, but you need something non-trivial that would be good enough to take in the log factor loss that we have. So anything that is from n to the c in the denominator here, you could have had, for example, log to the 5 d, and you would be fine. So you need to show this, and this is a linear statistic now. So earlier we were talking about some non-linear statistic of a log concave measure. This is a linear statistic of a log concave measure, and this follows from the theory of determinantal processes after some work. So and again, there are some edge cases which need to be controlled using some other estimates, but the bulk of the work is to prove a kind of correlation decay bound for the interlacing gaps of a Gelfand Tsetlin pattern obtained from a GUE minor process. So this is the high-level picture, and the open questions in this are firstly to extend this to other boundary conditions, and to understand what happens when so to get the local statistics also. So for example, if you take a random Gelfand Tsetlin pattern and you look at a little piece of it, there's something called a Bouthier bead process, which essentially has lots of beads and interlacing constraints, and they're random up to the interlacing constraints. And this is known to be the limit there. So are there similar limits for these hives? And also there's the integer valued story which relates to little Richardson coefficients. Can you prove concentration for these things as well? So then you will lose the Klartag basically, because it doesn't apply for lattice points in a polytope. It only applies for the wave measure on a polytope, but maybe some other techniques for. So that's it. Thank you. Thanks. Stop.